What if you could take a super complex, tangled network of connections and, just like that, reveal its core structure? Compressing it into these clean, understandable chunks. Well, that's the power of finding strongly connected components, and we're about to break down exactly how it works.
So, let's start with this. Imagine you're looking at a huge city map, but it's just filled with one-way streets. It looks totally chaotic, right? The question we're trying to answer is this. Are there districts hidden in this city where, once you drive in, you can get from any point to any other point and back again just by following the signs?
Okay, so here's the formal definition of what we're looking for. In graph theory language, those intersections are vertices, and the one-way streets are directed edges. A strongly connected component, or an SCC, is simply a group of vertices where you can find a path from every single vertex to every other vertex in that same group. It's all about mutual reachability.
So, let's bring that right back to our city map. Each SCC is basically a self-contained district. You might have a one-way street that leads you into the downtown district, but once you're in there, you can drive between the theater, the library, and the market, and you can always find a path back to where you started, all without ever leaving that district. These SCCs just neatly carve up the entire graph.
Now this is where the real magic happens. This is the big aha moment. If we simplify the map by taking each of our city districts, each SCC, and we just shrink it down into a single point, what happens to the map between them? Well, you're left with a much simpler road system, where all the connections are one way, and, this is the crucial part, there are no loops.
And that beautifully illustrates the most powerful property of SCCs. This new, simplified map is called a condensation graph, and it is always, without a single exception, a directed acyclic graph, or a DAG. And that makes perfect sense, right? Because if there was a cycle between the districts, they would, by definition, just be one big district, not separate ones. This acyclic nature is what makes SCCs so incredibly useful for analysis.
Okay, so we've nailed down what an SCC is. But how do we actually find these hidden districts inside some massive graph? Let's dive into the two brilliant algorithms that get the job done.
First up, we've got Kosa-Raju's algorithm. This one is often seen as the more intuitive of the two, mainly because its proof just flows so naturally from the properties of a depth-first search. It's a two-pass approach, kind of like surveying the city twice to get the complete picture.
So here's the game plan. First, you run a depth-first search, a DFS, on the original graph, and you keep track of the order that each vertex finishes its exploration. Second, you create what's called a transpose graph. By literally reversing the direction of every single edge, you're flipping all the one-way signs. And finally, you run DFS on this new transpose graph, but, and here's the key, you process the vertices in the reverse order of how they finished in step 1. Each tree you find in this second pass is one complete SCC. Pretty neat.
So, why on earth does this work? Well, it all hinges on this beautiful property from graph theory. The theorem basically says that the vertex with the absolute latest finishing time from that first DFS pass is guaranteed to be an async component. That's a district with no roads leading out to any other districts. So by processing in reverse order on the reversed graph, you're basically starting in that sync and cleanly grabbing the entire component. Okay, so if Kosa-Raju's method is the intuitive two-pass survey, Tarjan's algorithm is its clever, super-optimized single-pass counterpart. It figures everything out on the fly, all during a single exploration of the graph.
Now, Tarjan's approach is a bit more intricate because it's doing everything at once. As it explores the graph with just one DFS, it has to keep track of 3 key pieces of information for each vertex. Its index, which is just the time it was discovered, its low link, which is the index of the earliest ancestor it can reach, and a flag to know if it's currently on our exploration stack.
And this right here is the core of Tarjan's genius. An entire SCC has been found the moment we hit a vertex whose own discovery time is equal to its low-link value. This means that this vertex is the root of an SCC. It can't reach back to any earlier ancestors. When this condition is met, bam, we know that this vertex and everything above it on the stack forms one complete component.
So you might be thinking, which one is faster? Well, despite their really different approaches, 2 passes versus 1, a whole transpose graph versus a simple low-link array, both algorithms are optimally fast. They both run in what we call O of v plus e time, which just means they visit each vertex and each edge a constant number of times. They're both incredibly efficient.
So we have these two powerful algorithms, but how do they really stack up and where do you actually use them?
let's talk about the practical side of things.
This table gives us a great head-to-head comparison. Gozu-Raju, on one hand, needs 2 passes, and it requires extra space to build that whole transpose graph. Its logic, though, is maybe a little easier to prove from a textbook. Tarjan, on the other hand, is more efficient, 1 pass, less space, but its correctness really depends on you understanding that more subtle low-link idea.
And why does mastering all this matter? Well, because the interview frequency for this topic is high, for real. Companies want to see if you can understand and analyze the fundamental structure of networks, and SCCs are a classic way to test that skill.
So, if you're prepping for an interview, here's your checklist. Make sure you can do these 4 things. Implement both algorithms from scratch. Clearly explain why collapsing SCCs always gives you a DAG. Discuss those space and time trade-offs we just saw. And finally, be able to precisely define Tarjan's low-link condition. That's the key to identifying an SCC route.
And this isn't just for interviews, not by a long shot. SCCs are incredibly practical. They're used under the hood to find circular dependencies in huge software projects, to perform data flow analysis inside compilers for optimizing code, and pretty much to simplify any complex system of dependencies by boiling it down to its essential acyclic structure.
So there we have it. We've learned how to find the hidden, self-contained districts in any complex network. But that just opens up a whole new set of questions. Once you've identified one of those districts, how would you find the longest possible tour you could take inside of it? Now that is a fascinating next step in the world of graphs.